Great. Okay. All right. Thanks a lot. So let's get started. Robot audition, one significant part of my research right now. It is a quite challenging task to achieve, but we can also see that as an opportunity to design and create new methods that will be more efficient than what we have right now, and that can also serve different purposes that go beyond robot audition only. So, oops. Some of you might be familiar with robot audition, some not. To provide a very quick summary of what is robot audition. It is basically when we try to provide machines with hearing capabilities that are at least similar to, or if we can, even better than human. So as human, we use audio all the time in our everyday life. We have focused a lot in the last years on robot vision. And there's like a gap we would like to fill, where we would like also to provide audio sensing to robots, because that information is also very important to properly understand the environment around the robot. And speaking of that environment, it is a very challenging one. It is usually noisy. Most robots, at least some of them, work inside, indoor, so it's reverberant. And by definition, robots usually move, so the environment is dynamic. The robot will move from one room to the other, so the acoustic conditions will constantly change, and it's hard to predict what they will look like in the future. Something else that is very specific to robots is that usually we want to do computations online on the robot with little latency, and not to say real time. We want the computation to be done also locally. Some devices such as smart speakers are quite effective with speech recognition, but they usually rely on the cloud. So they basically push the audio recording to the cloud, it is processed, and then the reply is sent back to the device. Most robots, we want them to be able to run in any environment with or without an internet connection. So it has to be done locally. And because the robot is of a finite size and also has some limited power on board, we have limited hardware. So we have to be able to do a lot with very few hardware on the robot. And the thing is the following: if we can solve robot audition, then there are numerous short-term benefits. Obviously, in a few years, we do not expect that everyone will have a robot living indoor that they will interact with. However, some of the algorithms and systems we can design, if we try to achieve that long-term goal, we will design some methods that can be used in a short-term way. I talked about smart speakers, but there are a lot of applications like smart cars, some hearing aid for people with hearing loss, and so on. So these are all concrete applications that can benefit from this research at this moment. So I said previously that the environment was challenging. Why is that so? Well, right now, as I'm presenting, I have my headphones with a microphone that is quite close to my mouth. Actually, it's my AirPods, so microphone is a few centimeters away from my mouth. In a real life scenario with people interacting with robots, these people are usually a few meters away. That introduces a whole bunch of new challenges to be tackled. So in that example, we have a robot with many microphones, and we have people, speakers, a few meters away. Now, the first thing is you might have more than one speaker at once. So you have what we call some cocktail party effect. You want to isolate only a single conversation. And because we usually interact indoor, there's some reverberation on walls, ceiling, floor. So not only the sound wave reaches the microphone with the direct path, but there's also some reflections on these surfaces. So that definitely impacts the signal quality. There's also a whole bunch of noise sources in the room. You can think of fans, for instance, but also a TV set playing, some background music, and so on. So the robot has to be able to focus its attention on the speaker and ignore these interfering sound sources. And on top of that, robots are not static structure, they move. They will have actuators, and these actuators are sometimes very noisy. And not only they are noisy, but but also they are close to the microphones. So the microphones not only pick the target's sound source, but it also picks its own noise produced by the actuators, and we refer to that as a ego noise. So all these combined together make it very hard to use traditional approach to perform audio classification or speech recognition task, as we will normally do with a clean audio input. So, oops, sorry. So what are some of the tasks we would like to achieve when we speak of robot audition? One of the first tasks we can think of is sound source localization. So if you think about it as a human being, audition plays a central role in attention. Usually the first thing we will notice is that there's some sound, unexpected sound in our environment, and then we will move or turn in that direction to listen to that specific sound and also look at it. Indeed, I believe that audition plays a central role in evolution. It's a defense mechanism. So if you're doing something, you're looking elsewhere and you hear a threat, you will move your attention to that threat and use vision to also understand what's going on. So robots should have this kind of capabilities as well. If you call a robot by its name, you expect the robot to turn to you and start interacting with you. So that's one thing. Something else is obviously speech enhancement. So as I said previously, the environment is very noisy, and you might want to focus only on a specific sound of interest. So that sound is usually corrupted by noise. You want the robot to be able to extract the sound of interest and then process it with say speech recognition or something else. So speech enhancement also plays a role, is one of the popular tasks we have in robot audition. And also we focus a lot on speech, but we are aware that speech is not the only kind of signals that plays a central role in understanding the auditory scene. In fact, there are some other types of sound, for instance, animals or phone ringing, that can be relevant to pay attention to. So sound classification, to be able to say, okay, in my environment right now, there's speech, but there's also some mechanical sound. There's like I said, for instance, a doorbell ringing, a phone ringing, and so on. These are things to be addressed also when we think of robot audition. So sound classification is another task that we find relevant. So what I will do, I will go on some of these tasks and explain some of the research we did so far and how we achieve, how we were able to get the interesting performance for robots. So one of the first tasks I mentioned was localization. So to be able to tell where the sound comes from. This is not a new task. I mean, it has been done a lot in the past, not just with robots, but with general systems that use microphone arrays. So the goal here with microphone arrays is you have multiple sensors in space. You have sound traveling in space at a constant speed. And since you know the geometry of the array, you can measure the time difference of arrival of sound to each sensor, and then estimate what is the most likely direction of arrival of that sound to create those delays. And usually we like to break down the problem in a pairwise approach. So we look at each pair of microphone, for instance, here denoted by I and J. And what we assume in the simplest scenario is that sound travel in free field. There's no significant reflections. That hypothesis indeed is not super accurate indoor, but with a few tricks, it can do the job. And so we have what we find is that we can have these coefficients that we apply in the frequency domain to basically point a beamformer in a potential direction of arrival and measure the energy that comes from that direction. And the strategy here is to point this beamformer in every potential direction of arrival and only keep the one that leads to the most energy. So for instance, here what we do is we have this virtual sphere around the array that is our search space, and we will scan every point on that sphere. And for each point that we denote by index Q, we will compute the power, the acoustic power from that direction. Now, if you look at this big and scary equation, what it basically says is that you have to address each pair of microphone and you have to address each frequency bin. And these three sums has to be computed for every direction of arrival indexed by the variable Q. So in the end, when you do that full computation, you get a very important complexity proportional to Q. So the number of potential direction of arrival, the number of microphone, big M squared, and the number of frequency bins in your with your short time Fourier transform, big N. So that can imply a lot of computation, and this for robot audition can be prohibitive because, as I mentioned previously, everything has to be done online very quickly. So what I proposed a little while ago is to look at this problem from another perspective. Basically, these sums, all these operations can be summarized in matrix form. So you have this, what we call these super vectors, X and Y. Y contains all the power measured for every DOA, and X contains all the cross spectrum information for each pair of microphone. And in this case, W is a super matrix that incorporates all the coefficients. So we showed 2 slides ago this coefficient we proposed for free field propagation. So W basically has all these coefficients in one single very large matrix. At this stage, it's not very, I mean, it's the same mathematical operation. There's no gain in speed. But what we found is that what's interesting, that big super matrix W is actually a low rank matrix, and we can simplify it using a low rank approximation. So what we do is we run a singular value decomposition of that matrix, and we keep only the capital K biggest singular values, largest singular values. And we can decompose that matrix with the traditional SVD factors. And what's interesting is that K becomes much smaller than Q in most cases. And that implies that now we don't have to scan to do as many computation. We reduce the complexity to K times M squared times N. So as K gets much smaller than Q, we reduce the complexity, and the number of singular values we keep are in fact depend on the microphone array geometry. So the more symmetrical the array will be, the lowest, the fewest singular values we will keep. So in this case, in some configuration, we can reduce the number of computation by a factor that goes up to 300, which is huge, obviously. So the nice thing is we start with the arbitrary microphone array geometry, and this will often be the case for robots because robots have specific shapes. So we place the microphone wherever we can. We feed that geometry in the algorithm. It does the decomposition using a singular value decomposition. It saves the coefficients, and then it's ready to run online at a much faster speed. So the singular value decomposition is done offline only once. Usually takes a few tens of seconds, and then you're good to go. So that's interesting. Allows you to optimize your system to do a quick sound source localization. And we have some details here in the paper we published 3 years ago, where we explain all the little, all the bells and whistles needed to have this work properly. So that's one part of the challenge. Another part of the challenge, as I said, is speech enhancement. Speech enhancement, usually there are two end goals for that task. We have noisy speech, we do enhancement, and we have two choices. We can do automatic speech recognition, or we can do human listening. So by human listening, what I mean is, for instance, here I'm speaking to you with that Zoom interface. Right now, my office is quite quiet, but if there was some fan or some undesirable noise, there is some noise canceling algorithms running in the background, so that when you listen to me speaking, it is easy to understand each word, each phoneme I pronounce. So that's the end goal for human listening. On the other hand, if I take that audio stream and try to transcribe word by word what I say, provided that the ASR system can deal with my accent, we will achieve another task in this case. Now, what's interesting is that for human listening or automatic speech recognition, the enhancement is not the same. If we apply the same strategy for human listening and we feed that signal, that filtered signal to the ASR engine, we will most likely break the engine and it's not going to provide any useful information. In robot audition, we usually want to do ASR at the end of the pipeline. That's the end goal. We want the robot to understand the words that we pronounced. Now, why is it not the same goal? It's because when we do ASR, we want to avoid any nonlinear distortion on the speech signal. And to do that, and for human listening, we can afford some nonlinear distortion. So in this case, we have to avoid them. And one approach to do that is to use a microphone array with beamforming, such as MVDR, that you probably know. If we can do efficient MVDR beamforming, then we can feed that to the ASR engine, and it will produce decent results. Now, MVDR beamforming is one type of beamforming that requires what we call spatial covariance matrices, or SCMs. And we want to calculate a SCM for the target speech and SCM for the interfering signal, so maybe other speech or noise in the room. Once we have those these two matrices, and we have a pair of matrices for each frequency bin in the frequency domain, we can estimate the MVDR coefficient and we can apply the beamformer to the signal. Now, one strategy to estimate those SCMs is to generate a single channel time frequency mask, where we will identify which time and frequency regions are mainly occupied by the target speech and which one are occupied by noise. This approach is efficient, provided that we want to separate speech from noise, because speech and noise usually have quite different time frequency structure. However, if we have one target speech and different other speech signals, and probably also noise, it is very difficult to produce this time frequency mask because we have different speech signals, and it's hard to solve the permutation ambiguity, which which speech signal is the target one and which is the interfering one. So one thing we can do, and one thing we will do here, is we will use the direction of arrival of the target sound source as as a cue to tell which speech signals should be separated, and which one is the target one and which ones are the interfering ones. Oh, if someone has this microphone open, please mute your microphones. So yeah, so basically, if we already have a priori the target DOA, we can use that to generate the proper time frequency mask. All right. Now, the problem here is that with robot audition, as I said previously, on robots, the microphone array can take different geometry. And one of the reasons for that is because the robots have a unique shape, and we try to put microphones wherever it's mechanically possible to do so. So at training time, if we're going to train a neural network, we might not know the geometry of the final geometry of the array. And it would be very inconvenient to have to train a neural network to retrain it every time we change the microphone array geometry. It's very time consuming and requires a lot of data. We'll have to generate, simulate, or measure the new data with the new geometry, and will take a lot of time, would be quite difficult to deploy. So the idea we came up with is, what if we train a neural network for a pair of microphones, and we change the spacing between the microphones within a known interval. And once we have this building block, this neural network that can work on a pair of microphones, we can decompose the microphone array in pairs of microphones, apply this neural network to each pair, and then recombine everything together to generate a final overall mask that we obtain by either like computing the mean of all the masks, or doing the median, or majority vote, or whatever. But basically, we will divide the problem in a smaller one. We will compute the masks, and then we will generate a new global mask. And this is what we did for that project. So we started with the assumption we have, once again, two microphones. If you look at the top leftmost picture, we have two speakers, and let's say we want to listen only to speaker one. Now, in this case, it's the time difference of arrival is very useful, because these two speakers will have a different TDOA. So what we do is we take the speech signal, not the speech signal, but the recording of each microphone in the frequency domain, and we apply some phase shift correction to realign the signals with the speaker one here that we want to listen to. So we know that everything that is in phase with that direction is the target speech, and everything that is not in phase is basically the interfering speech. And we generate a target mask, which is an ideal ratio mask. We have the energy of the target speech, and we have on the numerator and on the denominator, we have the energy of both speech sources. And we can also include some of the noise from the environment, or even the ego noise from the robot. So that case is very useful. We have a clear separation between target and non-target speeches. Now, in some cases, when the microphone pair is aligned differently with respect to the speakers, we have the scenario at the bottom, where two speakers, even though they're not from the same position in space, with respect to the microphone pair, they will have the same time difference of arrival. And here it's an issue. I mean, there's no way we can tell which one is which using only the TDOA. And that's okay. We just apply the same approach, the same transform to the input. But then what we do is we assume that since we cannot make a decision on which speech source is the good one, we will simply generate a mask that will capture both speech sources, 1 and 2 in this case. And we can always try to remove noise, because noise has different time frequency shape. And we will have this target for this type of configuration. Now, what's interesting is that when we use that microphone array and we break it down to pairs of microphones, some pairs will allow us to have some discrimination between the speakers, and some will not. And that's fine. We will simply compute using the neural network we trained for a pair of microphone. We will compute the mask. By the way, the neural network, there are different architectures we can use. In the paper, we use a bidirectional LSTM. You could use potentially some UNet, some other architecture. The focus here is not really on the architecture, but the overall strategy that we deploy. So we generate those masks for each pair of microphone, and then what we do at the very end, we simply add all the masks together. And the nice thing is that indeed some masks will not provide useful discriminative information, but in the long run, when you add everything together, you will get some regions that will be always amplified by the mask, and these regions will for sure provide information about where the speech is and where the noise is, or undesirable speech is in the time frequency plane. And this is what we do. We sum all the masks together, and finally, what we can do is we can compute the SCMs for speech and noise. Now, we do assume we know the DOA and we know the geometry of the microphone array at runtime. So basically, we can convert the DOA into time difference of arrival. We feed that information to the neural networks. We estimate the overall mask for, in this case, we have 6 pairs of microphones. We get the SCMs. We estimate the SCMs for each frequency bin. And finally, we apply the MVDR beamforming method to generate the enhanced signal. And enough with the equations. Let's see how it works in real life. So what we did, for instance, we trained the network on pairs of microphones, and then we just generated a random, well, not random, I mean a new microphone array geometry. This one matches some of the commercially available microphone array. We have one source, that is the target source. We have another source that is the interfering source. And we use what we call our steer net to estimate the mask for each pair. And we use that with MVDR. And then we fed that to the typical Google speech to text engine. So let me show you. So first of all, we can look at the spectrograms. We have the reference source one, which is the target one at the top. Quite clean, I would say. And we have the speech to text result underneath the spectrogram. This was taken from LibreSpeech, so it's probably from a book. And then we have the mixture. We have the second source that is added to this, and we see that the spectrogram gets noisier as expected. And if we feed that in the Google speech to text engine, which is, by the way, a very good engine, it's still not able to properly decode the full sentence. And this is expected because now we have 2 people talking at the same time. So we see that we have some false recognition here. Prison until was not in the former sentence. Pipe and pepper were confused, and the end at the beginning is missing. So there are like a few mistakes in the text, the recognized text. And now if we enhance it, we get this spectrogram. If we compare it with the first spectrogram, we see it's quite similar to it. It's not perfect, but it's rather close to it. And if we feed that in the Google speech to text engine, once again, we get exactly the good sentence word for word. So let me just try to show you show or have you listen to some of the results. So this is, for instance, the reference. So there we go.
On again, and 2 hours later came in sight of the house of Dr. Pipt.
Okay, so that's the clean one. So that's the one we have at the top. Now we have the mixture with both speakers.
On again,
the prisoner
and 2
and his
hours later
escort were
came
on
in
their
sight
way
of
across
the
the
house of
prairies to
Dr.
the
Pipt.
Compton.
So obviously the male speaker, well, the other male speaker is masking some of the speech. We can, if we concentrate, we can try to recognize what's being said by the former speaker, but it becomes much more difficult. And this is what we get here in the second spectrogram. And you see that the prison comes from the prison word comes from the other speaker that we just added. And now that's the separated signal.
On again, and 2 hours later came in sight of the house of Dr. Pipt.
Not bad. I mean, we're almost done with the interference from the undesirable source. And the nice thing again is that all of that was done without any former training with that microphone array shape. It was all done with training on pairs of microphones. So we can apply this neural network to any microphone array now that it's trained once. So if that's this is just one example. We have complete results. We try different microphone array geometry, and we also run some additional audio samples. So it's all available online if you want to listen to some of the results, and even if you want to try the code yourself. This was produced for Interspeech less than 2 years ago, and the paper is also available online. And we call that network SteerNet because it's a neural network that allows you to steer in a direction of interest to listen to that sound. Now, one last thing. We talked about localization, but we also talk about classification. What if we can do both simultaneously? So if I have my microphone array, I have my robot in the environment, and the robot wants to pay attention to some of the sound from the environment. It wants to know what sounds are currently active and what is the direction of arrival of each of these sounds. So what we usually do here is we have this problem where each class, in this case, suppose we have 3 classes, one for speech signals, one for barking signal, and one for ringing signals. And we have 2 targets. One of them is a activity detection. So goes to 0 if the sound is not being played at that moment, and goes to 1 when the sound becomes active. And with the same class, we estimate a DOA. And we have that for each classes. So the nice thing with that architecture is that you can have, like in this case here in time, you can have different sound sources active at the same time, and you will provide hopefully a DOA for each of them. So you'll be able to localize simultaneously different types of sound. The downside of this architecture, as you probably guessed, is that if you have more than one source from the same class, suppose we have 2 speech signals, as it is designed for now, you're only able to localize one of them. And probably you will swap between one and the other because it's there's no, so far in the way the architecture is designed, there's no way to count the number of sources for a specific class and have different DOAs, but that's something we're working on to make it better. Now, once again, we could go with brute force, have this microphone array, finalize the shape, and just train with a lot of sounds that we will position at different places in the environment, and try to infer directly the DOA of each sound source. As you know, I'm not a big fan of training everything from end to end on those microphone array with fixed geometries, because this will most likely change when you have a new robot. So what we do instead, surprise, we split with pairs of microphones once again. So the idea is to use the signal in the frequency domain. We use the phase plays a central role here in localization. We get that that pair of spectra. We feed it to a CRNN, so a convolutional and recurrent neural network, and we want to predict the activity of each class, and now the time difference of arrival of each class. So not the direction of arrival anymore, but the time difference of arrival for that pair of microphone. And we have the same let's say approach with trying to detect everything at each time step for each class. So the only thing that changes here is that now we're trying to estimate the TDOA for each pair. And so we do that, we train the neural network, and then what we do is we once again break down the array in pairs of microphones. So we run the neural network on each pair, and we get the activity for each class and the time difference of arrival for each class for that specific pair of microphones. Now, in this case, for instance, it can seem very expensive to do that for every pair of microphone. You could skip a few pairs if you want. You don't have to do all the pairs. That's also the beauty of the approach, is you can choose how many pairs you pick, and you can do that online. So if your robot is doing additional tasks, you can decide to drop a few pairs to save on the computing power. But in the end, if you decide, for instance, to run all the pairs, you get all these predictions, and finally, you simply combine them together to get the overall DOA and the overall activity. So since you know the microphone array geometry at runtime, you can search for the most likely DOA, given you have all the TDOAs for every pair. And for the activity, you can do a simple majority vote to decide if overall there is or there is not some speech, for instance, some dog barking, some ringing. So you reuse that neural network that you train once for a pair of microphone, you reuse it on each pair for inference, and then you combine everything together, and you can predict the overall sound that is active and say where it comes from. So that was done for the decades challenge. Some of you probably know about it. We were the only ones to break down the problem with pairs of microphones. And funny thing is that we didn't win it, but we were in the average or strong team. So we got really similar performances to teams who use the overall array and use it as an end-to-end training approach. So what it says is that I do believe that most of the time you can break down the array in small pairs of microphones, and it worked as well. So we have a paper where we provide some details regarding the architecture and how we recombine all the TDOA together to get the direction of arrival. So in summary, we're still far from solving robot audition. There's still a lot of work to be done, but we know that we have some specific tasks that we want to solve. And I talked about some of them: so localization, speech enhancement, and classification. Now, what I like to do in robot audition is try to combine signal processing with deep learning to have some modular systems. So I try to avoid the end-to-end approach. And one of the reasons why I do that is because, as you realize, it's nice to be able to adapt to different geometries, because the robot shape will change continuously according to the physical properties of the robot, but also because it's easier to understand what's going on. Instead of having one huge black box, you have small boxes, and you can probe at different steps and see what's going on. You don't have to retrain all the time on the final robot. You can do some intermediate training for a smaller part of the problem, and then reuse that block in for that task. And usually it also makes the neural network simple, so it's faster to run. And as I mentioned, at the end, sometimes you can drop some of the pairs of microphones. You can decide that while you're running online, so you can free some processing if you need to. So robots can require a different amount of processing because they have multiple modalities like vision or other things that run at the same time. So you can cut some slack in the robot computing requirements if needed. And overall, there are still things I couldn't address in details. For instance, ego noise reduction. We're working on that at this moment. One of the challenges that the robot, each robot is unique. So you want to train a network to estimate the ego noise of a robot. But if you change from one robot to the other, the noise is different because the actuators are not the same. They're not positioned at the same place. So you have to retrain again. So we're trying to find strategies to avoid having to retrain all the time. So I think the takeaway message here is that robot addition, we cannot tackle this problem the same way we've been doing for the smart speakers or other systems that are, let's say, the mechanics of the system is known in advance. We have access to a powerful cloud, and the environment is rather static. These solutions are difficult to move to robots because the reality of the robots is quite different. So this is what we try to do here. And so obviously here's my contact info if you want to learn more about the projects and we are currently working on. And that's about it. I think I'm right on time, 45 minutes. So I guess now I can maybe stop sharing and answer questions, or maybe leave the share screen if we need to go back to some slides.
Yeah,